Okay, so hi everyone, my name is Tinkara Marija, and my team and I have been working... My team and I have been working on this project called Development and Characterization of LECA geopolymers under the guidance of the Kravania. We were founded by SHIUM project and European Union. So first, I will do the introduction and tell you the problem and the motive behind our project. Then I will tell you about materials and how we prepared our samples and characterization methods. And in the end, we will go through the results of our project and discuss them. Since 1950, the human activities have resulted in increasing the atmospheric concentrations of carbon dioxide. And earlier today, we heard in panel session that the cement industry in the European Union, I think, or maybe in Europe, was of 36% of the whole emissions of carbon dioxide. And according to International Energy Agency, the total emissions of cement industry will rise by 4% by 2050, as the whole industry's growth is estimated to rise 12 to 24% globally. Opposed to that, in recent years, vast amount of research has been dedicated to develop these sustainable building materials that could potentially be used instead of traditional concrete. And geopolymers, as we heard before, are a great alternative substance and material because they offer high mechanical strength and they have low carbon footprint. So the study goal was to develop and assess lightweight expanded clay aggregate in shorter LECA geopolymers. Geopolymers are made from the alkaline activation of aluminosilicate materials that are often sourced as industrial byproducts, as we heard before, for example, from Jesenica, like fly ash or slag. And as our aluminosilicate material, we used fly ash. It was activated with sodium hydroxide, 10 molar, and the agent was sodium silicate. And so in total, we prepared 5 different samples. And the first sample was a reference sample. It contained 100% normal aggregate and 0% LECA LECA grains. And each subsequent sample contained 25% more LECA grains and 25% less normal aggregate. So the final sample we prepared was used by adding 100% LECA grains and 0% aggregate. Our samples were prepared in 2 kilograms mortars and mixed according to a specific recipe, mixed for a specific time, and then molded in molds. The characterization methods that were used were, of course, for flexural and tensile strength, density, thermal conductivity, as we can see in the picture, X-ray diffraction, and SEM-DX. And in the end, we also conducted water vapor permeability tests. So the results of tensile and compressive strength, as we can see the comparison between them on the slide, we see a clear decrease in both strengths as the LECA content is increasing in our mixtures. The lowest compressive and flexural strength has LECA 100% sample, which is kind of logical because of the vaporous, porous and lightweight nature of LECA grains, and they make the material lighter and less strong because of the big pores that happen in the material. The tests were measured on the 2nd, 7th, and 28th day, as is also usually conducted for normal concrete. As you can see in the first sampler, the reference geo has high compressive strength. For reference, for those who don't know, the normal concrete usually has around 20 to 25 megapascals compressive strength. So geopolymers can achieve really high strengths, but with adding LECA, we can this ability to resist the bending force. Okay, so moving on to density and thermal conductivity measurements. Also here we can see a clear decline in both measurements. For the density measurements is the same as for the strength measurements, because of the porous and lightweight nature. Of course, reference sample has the highest density. And so with the thermal conductivity, we were pleased to see that LECA grains had this property of being thermal insulating. As we can clearly see, the thermal conductivity is decreasing with adding LECA grains. And so even though the adding of LECA grains is weakening our strength, we get some other good properties. Okay, so the result of X-ray diffraction is shown on this XRD spectrum. It is of the final sample, 100% LECA grain sample, and clearly we can see a high amount of silicium dioxide and then magnesium silicate, which was surprising, and we will see later on in SEM EDX results, how is it correlating to our samples. So if we compare these images, on the left is of the reference sample, on the right is of the LECA 100% sample. We can clearly see a difference. The reference sample has a clear side, and the LECA has a porous structure on the right side, which we were suspecting to be a grain. And we were interested in spectrum 3, 4, and 5 to see what was happening between the matrix and the LECA grains we added in each sample. We were suspecting that spectrum 1 and spectrum 2 on the right image were of similar structure as spectrum 1 of the reference sample. So if we compare EDX results, the upper table is for the reference sample, and on the lower side is a table for LECA 100% sample. And we can clearly see that if we look at the one on the lower table, on the spectrum 1 and 2, for example, carbon, we can see that it's similar to the upper table, and then spectrum 3, 4, 5, and 6 have higher content of carbon. Similarly to this, the silicium sample, silicium content, spectrum 1 and 2 have in the lower table for the LECA 100 sample, have higher content of silicium compared to other spectrums, and have similar spectrum to the spectrum one in the upper table. What was interesting was content for aluminium for spectrum 4 because it's suspiciously high. And so this was probably the result of some reaction of some new compound that was made in the reaction between the LECA grain and the other substances in the matrix. Okay, in the end, if we look at the water vapor permeability measurement, from reference sample until the LECA 75% sample, we can see a clear increase in our water vapor permeability, which is logical because of the porous nature of the LECA grains. And then there's a bit of a decrease in the final sample, which was unexpected, and there might have been an issue in preparing the tests or measurement. So in conclusion, if we add more LECA grains to our geopolymer matrix, we get reduced density and mechanical strength, but we also get enhanced thermal insulation and vapor permeability. So also LECA geopolymers support energy efficient and moisture controlled building applications, and they're very environmental and economic friendly by reducing carbon footprint and enhancing material performance. This is everything. Thank you for listening.